Hi again. So now we're going to do some examples of working with the idea of the E-log trick and general exponentials and general logarithms. So the first thing we'll start with is some basic examples. Compute d by dx of 3 to the 2x plus 1. And we'll compute d by dx of the log base 10 of x squared minus 3x. Okay, so there's question 1, and there's question 2. So for question 1, we're going to use the fact that we know that d by dx of b to the x is equal to b to the x times the natural log of b. What that's going to look like in the case where we have a chain rule is that d by dx of b to the u is going to be equal to b to the u times the natural log of b times u prime. Okay, that's what the chain rule says, because this is the derivative of the b to the x, and this is the derivative of the exponential part, the interior. So for problem 1, d by dx of 3 2x plus 1 is equal to 3 to the 2x plus 1 times the natural log of 3, that's the derivative of the b to the u part, times the derivative of the exponent, which means this entire thing is 3 to the 2x plus 1 times the natural log of 3 times 2. For question 2, we have a logarithmic expression. So the rules for log say that d by dx of the log base b of x is equal to 1 over x times the natural log of b. From a chain rule type expression, that would mean that d by dx of the log base b of u is going to be equal to 1 over u log b times u prime. If we apply that to the problem that we're working on, we get d by dx of the log base 10 of x squared minus 3x. Well, that's going to be equal to 1 over x squared minus 3x times the natural log of 10. Remember, we're not taking a derivative of the inside yet. That's just the derivative of the log base b to the u part. So you can see right here, there's no derivative of the interior of the function taken yet. That's multiplied on in the second part, times the derivative of the inside, which is 2x minus 3. So two basic derivative computations involving general exponentials and general logarithms. Okay, so for another example, let's look at one of these limits that we've been talking about computing. So let's look at the limit as x goes to 0 of x raised to the x power. So now I've got a variable expression in an exponent. And the trick to getting that down is to use the e to the log trick. Since I've got a natural log now in the exponent, I can use the power rule to take this x and move it out front of the log. And now I can use the continuity of the function e to write this as e to the limit as x goes to 0 of x ln x. And what I'd like to do is use L'Hopital's rule, but I can't do it yet because the expression that I have in here is not infinity over infinity or 0 over 0. It's 0 times infinity. As x goes to 0, the natural log goes to minus infinity. Okay? As x goes to 0, x goes to 0. So this expression is an 0 times minus infinity expression, which is indeterminate, but not one I can use L'Hopital's rule on. So I'm going to fix it. And the way I'm going to fix it is I'm going to rewrite it as e limit as x goes to 0. And instead of x, I'm going to work with 1 over x. So those two expressions are the same. But now I've got something where as x goes to 0, this expression on top goes to minus infinity. And the expression on bottom goes to positive infinity. And that's the sort of expression I can actually use L'Hopital's rule on. So now apply L'Hopital, which means that we're going to take the derivative of the top and the derivative of the bottom and see if we get a new limit. I'll write LH right there to let my poor, long-suffering professor know that I use L'Hopital's rule, so he's not confused when suddenly I've got 1 over x and minus 1 over x squared. That can be algebraically simplified into e to the limit as x goes to 0 of minus x. So if x is going to 0, this whole limit goes to 0, which means this entire thing is e to the 0, which is 1. So the limit as x goes to 0 of x to the x is 1. And there's really no other way to derive this limit except to work through a computation like this. The last example we'll talk about will be the sort of cutesy way that a math professor, some random math professor, might use to test your knowledge of how logarithmic and exponential derivatives work. So here's a pretty typical example. Integrate 5 to the x plus x to the 5th dx. Now that's just an easy question if you know your rules. Well, the integral of x to the 5th, that's easy. The integral of 5 to the x follows the other pattern, which is that the integral of b to the x is equal to b to the x divided by the natural log of b. So these sort of exercises are useful because if we're trying to guarantee that you know how these formulas work, one way of doing that classically is just to chain a whole bunch of terms together inside of the integral like this, where you have to distinguish between each thing in the list. Now, there are other exercises in this section that are going to involve using U substitution. I will leave those to you, but make sure that if you have questions about how those work, that you ask. All right, so that pretty much finishes up 6.4 star. We'll continue on to a new lesson tomorrow. See ya.